In section 2.3, we're going to evaluate limits analytically. In the previous section, we had two different types of approaches up to this point in order to find limits. They were like a numerical based approach, where if you wanted to find the limit as x approaches to c of f of x, then simply put, what we could do is make a number line, choose some values of x that are going to get successively closer to c, coming in not only from the left-hand side, but also from the right-hand direction as well. And we could use a table of values. We also saw how to determine the limits from a graph. So you can also graph the function and then visually inspect to see what the limit is that way as well. Now we're going to develop some analytical techniques in order to find limits. One of the things, and this is something that you don't want to lose track of as we kind of move through this section 2.3, we made a big deal about it that the limit of a function can exist and is independent of what actually happens to the function at the value x equals to c. Okay. However, there are some situations when the actual limit is going to be equal to the value of the function at that point c, and this is what we refer to right now in kind of air quotes as like well-behaved functions. Technically, the term for that is functions that are continuous at the point x equals to c, and that will be a topic for another section, but this brings us to theorem 2.1, which is some of the basic limit rules for functions. Let's suppose that b and c are real numbers, and let n be a positive integer. The limit as x approaches to c of a constant is simply equal to the value of that constant. So the limit as x approaches to c of the constant b is going to be equal to b. The limit as x approaches to c of x will be equal to c. This is one of those ones where it's kind of very well behaved. The function f of x equals to x is one of the nicest ones you can have. It's the identity function. You simply, everywhere you see an x, you can replace it with c, and that will give you your limit. And then the last one we're going to look at is the limit as x approaches to c of x to the n power. X to the n is a polynomial. It's a very well-behaved function. Therefore, the limit can be found in this case via direct substitution. As x approaches to c, the values of x to the n will approach c to the n. Let's take a look at example 1, get some practice for each of these rules. In example 1, part A, we want the limit as x approaches to 2 of the constant function 3. That should simply be equal to 3. We want the limit as x approaches to negative 4 of x. Again, polynomials are well-behaved functions, so you can just simply, everywhere you see an x, you can replace it with negative 4, so the limit is negative 4. And then the limit as x approaches to 2 of x cubed, this is going to be equal to 2 cubed. 2 times 2 times 2 should give us 8. So that limit equals to 8. Theorem 2.2 brings us some properties of limits. Again, let b and c be real numbers and n be a positive integer. And let's suppose furthermore that we have two functions such that the limit as x approaches to c of f of x is equal to L, and the limit as x approaches to c of g of x is equal to k. So both f and g have limits as x approaches to c. Then the following limit rules hold true. The first one is scalar multiplication. So if we're looking at the limit of a constant times a function, then it's simply going to be that constant times the limit of the function. If we want the limit as x approaches to c of the sum and difference of two functions, then the overall limit will just be the sum or the difference of the individual limits. The limit as x approaches to c of the product of the two functions will be the product of the limits. L times k. The limit of the quotient as x approaches to c of f divided by g will be the limit L divided by k, provided k is not equal to 0. If k is equal to 0, then there would be more analysis that would be needed. But certainly as long as the limit in the denominator is non-zero, then the quotient L over k exists as a real number, and that would be your limit. And then kind of a generalization of the x to the n we just saw a moment ago, we have the limit rule that says that if you want the limit as x approaches to c of some function raised to the nth power, if f of x has a limit as x approaches to c, then f of x to the nth power will have a limit, and that limit is going to be L to the n. So 5 very important properties of limits. In the next couple examples, I'll do a really thorough job of highlighting each of these rules and when they're learned and how they're used. But then once you kind of get practice with them and kind of get used to them, we can kind of just take them as commonplace. You don't have to necessarily show every single step every time. Let's take a look at example 2. They ask us to find the following limit. This is the limit as x approaches to 2 of the polynomial 4x squared plus 3. So let's take a look at what we have. First of all, this is the addition of two terms. So we know from our addition rule for limits that this is the same thing as the limit as x approaches to 2 of 4x squared plus the limit as x approaches to 2 of 3. This part here, we have 4 times x squared. That's a scalar times the limit. So you can pull that constant factor outside the limit as a multiplication. This is the same thing as 4 times the limit as x approaches to 2 of x squared plus the limit as x approaches to 2 of 3. And now we can use our basic limit properties. The limit as x approaches to 2 of x squared is simply going to be 2 squared. And then the limit of a constant is just the constant itself. So this limit here, as x approaches to 2 of 3, is simply going to be 3. We can now go ahead and evaluate this. This is going to be 4 times 4 plus 3, which gives us 16 plus 3, which is equal to 19. So overall, this limit is equal to 19. And it doesn't take too long to realize that essentially, how do we get that limit of 19? Well, because polynomials are well-behaved functions, according to our limit rules from below, you can simply find this limit via direct substitution. So this is one of the rare instances where direct substitution does work. Everywhere you see an x, plug into 2, and we get the limit of 19. Polynomials are not the only class of well-behaved functions. For example, any rational function, which is the quotient of two polynomials, is well-behaved provided the denominator's limit is not equal to 0. What that means for us is that we can find the limit as x approaches to c of any polynomial p of x simply via direct substitution. Everywhere you see an x, put a c, and that function evaluation will give you the value of the limit. Similarly, if we have a rational function where the denominator is non-zero at x equals to c, then the limit as x approaches to c of r of x can be found by simply taking and evaluating the function r at c. So everywhere you see an x, put a c, and that would be the value of the limit. Let's take a look at example 3. We're asked to find the limit of this rational function, the limit as x approaches to 1, of x squared plus x plus 2 divided by x plus 1. This is a rational function. X is approaching positive 1, And we notice that positive 1 will not make the denominator 0. So according to our previous limit result, we can find this limit via direct substitution. Everywhere we see an x, let's put 1. This is going to be 1 squared plus 1 plus 2 divided by 1 plus 1. This is going to be 1 plus 1 plus 2 over 2, which is equal to 4 over 2, which gives us an overall limit value of 2. So the limit as x approaches to 1 of this rational function is equal to 2. Radical functions are also well behaved where they exist. Let's suppose that let n be a positive integer. The limit below is valid for c when n is odd and c is greater than 0, and also when n is even. That is, the limit as x approaches to c of the nth root of x will be equal to the nth root of c. So we can evaluate limits of radical functions by direct substitution as long as that radical is defined for that value c. And then a big result, which will be very useful, is the limit of composite functions, which we'll do next.